then Richard, the stage is yours.
Thank you for the introduction. So this talk is basically based on a paper that was just accepted and is to be presented on the ACM-BSc-I 2024. And we're moving a little bit from permissionless systems where we have probabilistic consensus finality to permission consensus. So usually you have absolute consensus finality, you have a higher throughput and lower latencies, but also usually not as good scalability. So the motivation is, of course, that you can build secure and critical infrastructure using state machine replication. So as I guess most of you know, it works like a client sends a request to a server, but instead of one server, you have multiple servers, so that if some of them fail, you still have a working system. Typically, there's an agreement on the request order of this requests. So you have reliable replication, and if it's Byzantine fault tolerant, then it's especially reliable. So as someone said before, typically these systems are pretty costly, so we have applicability limitations due to this processing and communication overhead. And there's been a lot of work in the recent years to optimize this, and one of the layers is of course the networking layer. So there has been a focus shift, more work focusing on network and transmission, for example, to improve dissemination of client requests or also general consensus message communication. So in the previous work, we already identified different layers or assumptions that a lot of different systems have. So it basically goes into the same argumentation that we already heard. So a lot of systems say, well, they want to have reliable communication, point-to-point interconnections, and authenticated messages. But what then happens is nobody specifies it, and typically it's just implemented by TCP/IP, some signatures and/or TLS. So our goal was parallel to Cyan, basically, but instead of building a completely new infrastructure, we were interested in evaluating existing network transfer protocols and secure channels, and if there's a possible optimization space for BFT-SMR using these. For the evaluation, we of course need to choose an example. So for our system, we choose HotStuff, which is a permissioned leader-based BFT-SMR protocol for partial synchrony. It's base for significant ongoing research, and a lot of other systems are assuming HotStuff or building on it, and it also employs the typical SMR optimizations such as comment batching and pipelining, but the structure is still pretty simple. So HotStuff looks roughly like this. You have the client, which sends the request to all the replicas in the system. Then you have multiple phases of a broadcast vote pattern where the leader sends a proposal to all the replicas vote. And then in the end, if the request order has been agreed on, all the replicas will answer to the client, and the client will receive enough answers and consider the request to be committed. So what about the transfer protocols? If you're not using Cyan, then you might end up with the typical protocols that you might know. So UDP as an unreliable protocol, TCP or SCTP as reliable protocols, either with a byte stream or providing datagram-based transport. There's also QUIC, which is connection-oriented, reliable, and built over UDP. And it's mostly been prominent in the web context, where it helps to improve performance by avoiding head-of-line blocking for multiplex connections, and it also offers integrated TLS negotiation. However, in our HotStuff context and the communication structure, we actually don't really have these characteristics. So in our effort to study a simple protocol that has less overhead and is still reliable, we went with an idea from related work to implement basically a UDP-based protocol with reliability and ordering on application level that just mimics TCP RTT estimation. We call this RUDP for our evaluation. So the second part are the secure channels that we want to look at. We already heard it. Typically, what you would use, and I guess what most of you know, is TLS. So it's a secure channel that assumes reliable in-order transport under it. So you would usually use it with TCP or SCTP. Data is exchanged in typed records, and the record processing is always done in order. The unreliable pendant would be DTLS, which can also be used over unreliable protocols such as UDP, but it comes with extra cost for extra header fields, but it in theory also allows for independent record processing. Some general networking background for those of you who don't know. Typically, of course, messages don't flow over the network magically, but there's limitations, for example, the maximum transmission unit. So all the transport layer protocols need to take care that the data is split up sufficiently into fragments and segments. If you're offering a reliable transport, then of course you have retransmission and state keeping going on. And if there's in-order processing, such as for TCP or TLS records, then if a segment is lost, then the rest of the stream may stall. So why am I introducing all of this? Because the core insight that we already heard before is that you cannot just simply assume that your BFT-SMR protocol will be running just by saying, well, we have a reliable transport, but there's actually a plethora of different layers under it that need to work for everything to run smoothly. So on table 1 here, we can see a selection of different elements that need to be fulfilled. So for example, on the client layer, the client would only progress if he gets enough matching answers on his requests. Simple replica would, for example, it needs to receive the current proposal in order to vote. A leader needs to receive enough votes to progress, and so forth. So the core insight is that successful replication depends on the successful completion of all of these layers. And since BFT-SMR can tolerate at most parallel failures, these can happen, of course, at any of these layers before the final request or latency would be delayed. If we have additional optimization strategies, such as batching or pipelining, then this also potentially increases the delay impact because it's not just a single request that gets delayed, but it's a whole bunch. Okay, so what we were interested in is to see if there's any differences between typical transfer protocols, and we want to quantify this somehow. So what we did is we implemented these 4 transfer protocols, TCP, UDP, RUDP, and SCTP, with and without secure channel in the publicly available hot stuff proof of concept code base. And we're aiming for 3 target evaluation points. So first of all, we want to make sure that in our measurements, we actually completely saturating the consensus system and the client is not the bottleneck. Once we have ensured that, we want to check the impact of the protocol choice with and without secure channel. And finally, we want to check the impact of the transfer protocol under loss. The setup that we used is the setup is built from hardware machines. So all of our experiments have been running on hardware machines from a heterogeneous setup with 3 hardware groups connected by switches. And all our experiments for experiment isolation are using a single client and a single leader on the most powerful nodes for up to 5 faults or 16 replicas. And we use or measure the typical BFT-SMR metrics such as latency and throughput, and vary a set of BFT-SMR parameters such as batch size, payload size, replica number, and also possible packet loss. For the non-loss setups, we also clear the experiment for outliers. For the less setups, we don't, so we don't lose any interesting outlier data. So finally, the setup looks something like this. We have a single client that talks to all our replicas, and then we vary basically the connections between the replicas and study the behavior. All right, so for our first goal, we want to check the impact of input request saturation. And what this means is basically we want to determine the batch size for which a certain number of clients are actually saturating the system, so we can be sure that the consensus or the replicas are the bottleneck and not the client. So on the left-hand side, figure 5, we see replication latency over batch size. On the right-hand side, figure 6, we see throughput over batch size. And we can directly see that for a single client, a batch size of 50 is enough. So for larger batch sizes, throughput doesn't increase. So this is basically our saturation point, which we can assume where for larger batch sizes, the client would be the bottleneck, and for smaller batch sizes, the replicas would be the bottleneck. Knowing this point, we can then continue and check the actual impact of different transfer protocols. And the first rather non-interesting answer as well, the impact without any modifications is not that big. So in figure 7, we see the latency over batch size again without secure channel. In figure 8, we can see latency over batch size with a secure channel. And we can directly see that there's basically no significant difference in our setup between the transfer protocols without the secure channel enabled. If we activate the secure channel, we have a small latency increase, and the DTLS-based protocols perform relatively worse due to the DTLS overhead. Well, here we checked it for batch size, and we already know that in this area, basically the client becomes the bottleneck. So what about scaling? Let's take a look at how the system looks, or the behavior looks for different replica sizes. So again, the left side, figure 9, we have the latency of a replica number, and without secure channel. On the right-hand side, figure 10, latency of a replica number with secure channel. The picture is pretty similar, so we have no significant difference between the transport protocols without the secure channel. Similar behavior for activated secure channel, and the actual latency growth for growing replica numbers can be directly explained by the ratio of honest nodes that are required for the leader and hot stuff to progress to the next phase. Okay, so far so good. So we can see that without loss, there's not much impact. What happens if we actually apply a loss to our network? So here, left side, figure 11, we have the latency over the uniform loss on our links. On the right-hand side, we have throughput over uniform loss on our links, and we can directly see multiple things. First of all, we see that above 1% loss, the variance significantly increases. So this is directly caused by inconveniently placed losses, so loss cascades, which can trigger in a BFT-SMR protocols things such as a leader rotation or application level timeouts, hence the large variance. We already see that for 1% the performance is roughly halved, and for 2% loss the performance is already slowed by an order of magnitude. For values below 1% loss, TCP in general outperforms the other transfer protocols, for example SCTP by 17% for 0.25% loss. And this is due to different retransmission timeout configurations and also different availability of hardware offloading. So we will talk about the RTO later on. What about scaling? Well, if we take a look at loss impact over scaling, again, we have the latency over increasing replica numbers, this time sorted by different batch sizes. We can see that if the client is the bottleneck for larger batch sizes, this increases the latency. In general, if we have a very small batch size and a small replica number, then we can see that for this edge case, actually, the low overhead protocol RDP outperforms the others because of its small protocol overhead and better adjusted RTO. For larger replica number, we see that the protocol differences are actually becoming less, and this is due to the bottleneck, the CPU and bandwidth bottleneck, shifting towards the single client process that we're running. So we're talking already about the impact of this RTO value. So let's talk a little bit about this. So if we have inconveniently placed packet losses in our network, then this can prevent our transfer protocols from acknowledging data or retransmitting our requests, and this can cause a retransmission timeout. So if the sender doesn't receive an acknowledgement for a longer time, then he will retransmit the unacknowledged data after this timeout. The main thing here is that the typical timeout, or for example, the TCP minimum RTO is around 200 milliseconds, and in a smaller setup, this is orders of magnitudes larger than, for example, the typical hot stuff replication latency, around 10 milliseconds in our setup. So the goal was to check if this RTO configuration impact has a suitable impact or has a positive impact. For this, we use our SCTP-based implementation because the SCTP socket offers a direct interface for modifying this. We defined 4 different profiles, so the standard SCTP profile, then a profile that mocks the general TCP values, and then 2 profiles with a flat value of 150 milliseconds across all the values, so the initial, the minimum, and the maximum value. So if we check these and measure the results, what can we see? Again, figure 14 on the left-hand side, we see the latency over loss percent. On the right-hand side, we see the throughput over loss percent. And we see the general behavior that for larger loss percents, the variance increases rapidly. But we also see that for the more stable loss range, the suitably configured RTO value, which is closer to our actual network round-trip time, shows consistently better performance. So what about scaling? If we do the same measurements for the RTO profiles for varying replica numbers, here in figure 16, again, we have the latency over increasing replica numbers for different batch sizes. We see this time for 1% loss, by the way. So we see again, for larger batch size, where the client becomes the bottleneck, we have a generally increased latency. For larger N, again, the protocol differences generally become less. But again, we're confirmed that a smaller retransmission timeout generally outperforms the larger retransmission timeout because it is closer to our actual network latency. We can also see some outliers here, which is due to the larger loss rate. And again, for our loss measurements, we didn't clean for the outliers to not lose this data. Finally, what we want to do is we want to argue which part of the RTO causes this. And it's actually the minimum RTO value, because usually the RTO is adjusted to the actual network conditions. So here we have a histogram plot of the latency of our client requests plotted over the transaction throughput rate that they were actually completed with. On the left-hand side, we have it for our default profile. On the right-hand side, we have it for our S50 profile. What we can directly see is that the S50 profile shows an overall higher throughput and less latency spikes. And we also see these funny latency plateaus around 1,000 milliseconds, 200 milliseconds, 200 milliseconds, and 50 milliseconds. And these are actually the minimum RTO values of our profiles that cause these large latency spikes if an RTO occurs. So to sum up, for our measurements, we need to make sure by our parameter choice that we're shifting the bottleneck into the right direction to make sure that our measurements are precise. If we're using a secure channel, then this imposes a small performance overhead where DTLS is more costly, but it's still a viable choice if you're implementing a medium-sized network. For the transfer protocol differences, we actually only found significant differences if we're operating in a lossless scenario. In our scenario, we found TCP to be the best default choice, both because of its performance and also because it's widely available, well studied, and has usually available offloading support in hardware. There might be setups, for example, small replica numbers or smaller payload sizes that benefit more strongly from a protocol that has a smaller protocol overhead like UDP. And if you're actually operating a BFT-SMR system that has frequent reconnections between replicas or actually uses multiplexed connections between replicas, then the protocol might benefit from QUIC. In terms of loss, we saw that loss values above or equal to 1% already introduced considerable variance and performance reduction. And for loss values above 2%, we saw reduced system performance by approximate an order of magnitude. Finally, regarding the RTO, we found that if we adjust the minimum RTO to your actual network RTT, then it can improve performance. So if RTOs occur and the minimum RTO is larger than your actual round trip time, then you should try to optimize that if you know these dates or this characteristics about your system. All right, so to conclude, we conducted an analysis of secure channels and network interdependencies in context of permissioned BFT-SMR. We studied the typical transfer protocols as a possible optimization space and evaluated for general transfer protocols and two secure channel implementations for the scenario using hot stuff. Key takeaways, as already presented, the performance and robustness of BFT-SMR heavily depends on the functioning network below. So it's not enough to just say, well, we have this reliable connections that are somehow realized, but we don't care how. We saw that transport and secure channel configuration impact BFT-SMR already for small replica numbers and loss. And we also saw that just changing the transfer protocol or its configuration is not actually sufficient to enable sufficient performance in a high loss environment, and you need to take a different road. So for example, using Scion. And in that sense, finally, it's always functional to adjust consensus and transfer protocol timeouts to match the actual values of your system timing, to match them as closely as possible. For future work, we would like to check the optimization potential of other potential BFT-SMR building blocks, such as cryptographic primitives and their impact on scalability and performance. That's it, and I'm open for questions.
Thank you, Richard. Okay, as you had the extra brainstorming time, what's the amazing question that someone thought of? If not, maybe I quickly can start. I'm an IoT guy, so for me a loss rate of 1 or 2% is usually not something I'm scared about. Do you see a trend that such protocols become broader in the application scenario? Because we saw how nice it would be if everything works out, but there will be probably more heterogeneous aspects in network topologies in the future. Cyan on the one hand side, but also very lossy things, maybe with very low energy aspects. Then, do you see a chance that we get more flexible in this domain?
Well, flexible, I mean, first of all, regarding the scope, I would say these findings don't really apply to like a geo-distributed VM setup where you have widely varying latencies, right? So it's more about medium-sized setups that are not a complete data center setup where you could run something like RDMA, but it's more exactly for these heterogeneous setups where you might have a subnet of multiple nodes with different hardware specs that have a somewhat more predictable behavior or predictable latencies than this completely geo-distributed VMs. So, and of course the impact of the modification will definitely depend on the actual values or the how good you know your system, right? The better you know your system, the closer you can adapt the transport configuration to the actual values of the system. So yes, I'm not sure if I answered the question.
You gave me hope.
Okay.
Cool, thanks. There's a question.
Did you also look at other consensus protocols, like some of the successors of hot stuff, or do you have a sense if they behave the same or very differently compared to your results here?
We didn't actually implement other protocol or other consensus protocols, but I would say that the general structure, if you're operating a leader-based consensus protocol, then the general weighting regime is the same, right? Because you have always this lockstep communication where you have if you have multiple leaders, then arguably the overall throughput over the overall performance might be better. But if you're only looking at one single leader, then the mechanics in principle stay the same. So my conjecture would be that, for example, having multiple leaders alleviates some of the problems, but the underlying principles, so to speak, would still apply. That would be my conjecture, but we didn't actually measure it so far.
Thanks.
Yeah.
Any further questions? Yes.
Did you test for different congestion control mechanisms in TCP, or just went with BBR, I guess?
No, we actually went with Cubic, and there's work going on testing this right at the moment. Maybe a first sneak peek. There are differences, but they are not that big, at least for the studied values.